SwayamPrabha. Digital India. Educated India.
Welcome to week 10 of this NPTEL course on muffler acoustics. So, we are heading towards the towards the end of this course. Well, but there are quite a few interesting topics still remaining, and that will be covered. I will try to cover as much as possible in the next 3 weeks, and we will probably next week we will touch upon the 3-dimensional analysis probably for the first time for simple muffler configurations. But in this week the idea of the basic contents for this week is to analyze multiply connected muffler systems, basically those muffler systems in which the wave propagation path can be non-unique. So, let me just draw a few muffler configurations and try to prove the point that what do we mean by multiply connected mufflers and or just cascaded systems, what is the difference. So, all this while some of the commercially available muffler systems, I mean the ones that are used in sort of a commercial mufflers, they definitely have perforates, as I have been sort of insisting. So, they sort of appear something like this, So, I am sort of drawing here, I am drawing here I am drawing here a cross flow perforated element which is open ended, something like this. So, here the waves have really no choice but to go through these perforates and pass on through these 2 perforated pipes 1 and 2 and then leave this outlet pipe. So, this is the inlet and this is your outlet version. So, the waves have to go like this. Now, another thing is if you were to do it something like this, okay. So, if you kind of close it, so it becomes closed ended or cross flow element still, but it is no longer open ended, that in the sense that the waves no longer discharge here, but still the waves have to go through these elements. We can keep adding more and more complexities to it. We can have a kind of a dissipative lining. So, this is just one such configuration in which the waves have to kind of go through one path, or else you can have another configuration. One configuration that we have been kind of analyzing so far is obviously your straight through configuration, which obviously has only one way in which the waves can go through the system. So, waves can only go through like this. You can keep adding complexities. For example, one can always put a kind of a plug here as we analyzed, or perhaps what also can be done is something like, well, you can have this and you can have a dual kind of a configuration, okay, and then with extensions or with partially perforated things, and then you can keep adding complexities like putting a dissipative lining, okay, and then the flow goes. So, but the central thing to be noted in this configuration, let us say well, this is cross flow anyways, cross flow configuration, and this is straight through. So, the idea really is that the flow can take only one path, okay, but then there can be many other configurations in which multiple paths do exist. For example, let me go to the slides of the week 9 lecture. So, in this I briefly alluded to the fact that waves apart from they have to the flow enters here and it leaves sort of here. So, in the process the waves can either take this path, and if this path tube weren't there, okay, so then the waves can directly come and they can go like this also, and they can actually come and straight away go like this. So, basically the idea is that the waves have multiple paths through which they can go, and what we probably can do is analyze such I mean, this is just one motivation that why do we study multiply connected mufflers. You can synthesize a number of configurations in which the wave propagation path is non-unique. So, let us analyze that using a simple network analysis approach and first characterize them using impedance matrix approach, which we will probably introduce it for the first time in this course. And let us first analyze what do you mean by a a simple muffler configuration, which makes it very sort of crystal clear that what would a multiple wave propagation path look like. So, let us consider a simple duct like this. There is a pipe and the flow goes like this. So, here you have your, let us say the waves come here and they are split into this part and this part, and then they go like this and the flow again attaches here, and then there is a downstream thing. So, now compare this with the configuration, a simple pipe in which the waves have to go only along this path. Okay. So, what is the difference between say A and B? Here the waves can go have alternate path to reach the downstream. This is the upstream point, this is the downstream point, same upstream, downstream. So, the waves can have multiple paths through which they can go. Okay. So, one needs to do something different to analyze or to relate the state variables between u and d, that is p u, v u and things like this. One needs to do something different to analyze such a configuration. So, we are going to study all that is going to happen now. Actually, these configurations are typically called, such pipes are called Herschel-Quincke tubes, HQ tubes, HQ tubes. So, what happens before I discuss something else? So, what does what does this additional part do? So, this pipe, let us say the length is L2 from this point, and from this point it is L1. Okay. So, because of the difference in because of the path difference, they at certain frequencies there will be a constructive interference happening between the waves, and at other frequencies there will be destructive interference. What it means is that the waves that come here at certain frequencies, they add up to basically increase the amplitude, or basically result in significant increase in amplitude. As a result, the transmission loss of such a system is basically becomes almost acoustically transparent system. But at other frequencies where destructive interference happens between these pipes, at such frequencies almost negligible acoustic power is transmitted downstream, and because of this resonances, at certain resonance frequencies where such destructive interference happens, these HQ tubes perform very well. You get a spike in the transmission loss curve, what they are called attenuation peaks. If you compare this with the transmission loss for a simple pipe with no expansion contraction, obviously the transmission loss is 0 throughout the frequency domain, but just introducing this path difference would lead to multiple resonances. We'll do a proper derivation of that. And another system that is there is basically, for example, if you have a muffler system like this, as we have been discussing in the beginning of this course, a very simple looking concentric muffler configurations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can, what one can do is that to relate things from P1, V1 to V10, what we could do is basically get T12 and between 2 and 3 for a stationary medium it is related by a identity matrix, if you recall. So, it will be basically 2, 3 is identity matrix. So, one needs to write between the transfer matrix between 3 and 4. Okay. Like this, if we keep multiplying, we will get the things between T 9 and 10. So, effectively what will happen is that T overall matrix will become T12, T34, and assuming that T23 is I matrix identity, and T56, T45 is again an identity matrix, and then T67 is again an identity matrix, and then you will have your T78, T89 is again your I matrix, and then you have your T910. What exactly am I trying to say? What is the message that I am trying to convey? For a typical commercial muffler, you typically have two muffler shells attached to each other, one is upstream and other is downstream, and internally you can have a very complicated structure here and very complicated structure here. But now still the wave propagation path is unique from upstream to downstream. But now let me sort of just rub all these things and introduce another path to the wave propagation. So, let us say what I am going to do is kind of just also get rid of these numbers and introduce this thing something like this. Well, okay. So, what happens now, the acoustic waves, they have more than one choice of propagating. So, they can, at the moment they come here at this junction, they can either propagate downstream here or they can go here, and then when the waves come here, they again have a choice of constructive interference and destructive interference. So, this can be your muffler proper or muffler 1, muffler 2, and what we are doing here is providing additional path through which the waves can go. So, such things are called multiply connected mufflers or things with non-unique wave propagation path. So, what is the difference between this system and the one that I had drawn earlier, or just between when you have just two mufflers connected without, if this tube weren't there, if this was a solid pipe, solid something like this. What is the difference? Cascading that was used previously now cannot be done, because essentially the idea of transfer matrix multiplication or cascading is really that the wave propagation happens in a one direction, and you can just multiply out the matrices to relate things from upstream to downstream. But because of the very complicated intricate nature of muffler systems in a commercial vehicles like the one that I had shown previously, multiply connected perforated mufflers, or even the systems that are used in heating, ventilation and air conditioning system, where you have multiple side branches or complicated intricate networks in gas pipelines. So, there non-unique wave propagation path does exist, and so that basically there is quite a bit of a motivation for us to deal with such a topic here, introduce it, and of late there has been there is quite a bit of research in this field, we will come to it. And so, let us kind of analyze perhaps the most simplest of a multiply connected muffler system, which is this one. Now, before I begin the analysis of say the system shown here A, what I would also like to sort of mention is that this element, this one, this is the 2 port element. Let us call this as 1, this is element 2, this is 3, 4, 5 and 6. So, we assume that 5 and 6 have coalesced and 1 and 3 have also come together. So, this is essentially a very small one point really, I am just drawing it separately just for better conceptualization. But what I am trying to say now is that this element, this guy is a 2 port element, because they are only inlet port or outlet port, or it is best not to talk in terms of inlet and outlet, just 2 ports, where either you can relate the pressure and velocity is here to the pressure and mass velocity is here, or else you can relate the pressure, acoustic pressure here and here with the mass with the respective mass velocities through an impedance matrix. And as I briefly talked about in the last few lectures of week 9, this impedance matrix thing is a beautiful concept, because now we do not have a compelling, we do not have a kind of a constraint that the system should have only even number of ports. It is not necessary that you have a muffler system with only 2 ports, you can have 3 ports also. In such a case, impedance matrix is very useful for characterizing the system, and then we can do some network analysis, which anyways we are going to do now. So, for a simple 2 port system, and then we will consider another test case. So, here for such a pipe here, another 2 port element is this guy. So, I would write this as TP1, 2 2 port 1, 2 port 2 between 3 and 5, and then junction laws will apply. So, exactly you have your Kirchhoff's law for current. So, basically current is basically redistributed into number of paths, number of sub circuits which comprises an electrical network. So, here also we can redistribute, write mass velocities as being split into number of paths, which we will talk about now, and at the same point voltage is the same. So, what we will do is that we will equate the pressures, at this point 1, 2, 3 where they have come together is a very small point, P1, P2, P3 tilde, they are all the same. So, these are junction laws. So, junctions are really points where 2 or more elements are connected together. So, those elements themselves can be a 2 port element or a multi port element, we will soon sort of figure out, but depending on the network involved. But for analyzing such a system, what we will do now is basically let us write down the junction laws. So, here we will write this as P1 is equal to P2 tilde is equal to P3 tilde, and your velocity gets split into 2 parts. V1 that comes here gets split into V2 tilde plus V3 tilde. Okay. It gets split into 2 parts. And another thing that you have is the let us first get done with the junction laws. So, P4 tilde is equal to P5 tilde is equal to P6. Okay. And velocity that acoustic waves that come here, they all contribute. So, V4, note that V4, all these V's are mass velocities, or you can also have volume velocities if you divide it by density. I choose to work in mass velocities. So, that is what is constant. So, V4 plus V6 is equal to this thing. Now, note that the wave propagation direction is such that in velocity at the inlet of the muffler or at the assumed inlet, the velocity is taken into the system positive, and at the outlet the waves that the velocity is taken positive in the direction facing outside the system, that is towards this side. But we can use another sign convention also later perhaps, but for now we will probably stick to this convention, because the reason being is that we already know the transfer matrix from 2 to 4 relating things from 2 to 4 V2 P2 P2 V2 can be written something like this. So, I am just writing C, let me call this length as L2 and this as L1. So, I am writing this as C2 J Y2 S2 and J Y2 S2, and this is C2, and this is P4 V4. Okay. So, this is what it is. This is the transfer matrix here. I will call this equation as say 1, 2 and 3. Okay. Now, the transfer matrix that relates 3 and 5 would be something like this, P3 and V3 tilde is equal to what? C1 J Y1 S1 J by Y1 S1 and C1. Okay. And this is P5 and V5. So, we have now the relevant number of equations, let me call this as 4. Now, how many variables we have? That is given by the number of nodes we have for such a system. That is the most general analysis that I am trying to present. So, 6, 1, 2, 3, 4, 4, 5, 6. So, 6 into 2, 12 variables we have, including both pressure and velocity, because at each port there is 2 variables. Okay. And how many equations do we have? 1 and 2, because this one and this one, they are together form 2 equations, and plus this one. So, 3. Okay. So, 3 plus 3 6, 6 plus 2 is 8, and 8 plus 2 is 10. So, we have 10 equations. We have 10 equations, all right, 12 variables and 10 equations. So, what does it mean? That any 10 variables you can express in terms of the remaining 2 variables by theory of general linear algebraic equations. ultimately what we want, like I said, cascading cannot be straight applied here, not in the straightforward manner. So, what we can do is that adopt the following practice. We can rearrange the system in a certain manner in a network analysis. So, now we are properly entering into the network analysis. So, what we do, we choose to represent P1 V1 in terms of P6 V6. Alternatively, we can also represent P6 P1 and P6 in terms of V1 and V6, but let me just move ahead with the transfer matrix formulation, nothing different to what we have discussed in the preceding lectures. There are large number of permutations one can do. We can, just like we have put here a transfer matrix relation in equation 3 and 4, we can also relate the ports 3 and 5 or 1 and I guess 2 and 4 using an impedance matrix. We will slowly cover that and see what are the pros and cons of that. But for now, let me just write down your P1 matrix. I am just dropping the tilde signs for simplicity. So, P1 V1 P2 V2 and eventually at the end of the day we want P6 V6, is not it? This would be your 10 cross 10 matrix, and this would be your also rectangular matrix 10 cross 2 matrix, and here you have your P6 and V6. Okay. And let me just sort of start making things like rows and columns 3, 4, 5 like this, 1, 2, 3, 4, 5, 6, 7, 8, and then we can probably add one more 9 and possibly one more here 10. So, and then 1, 2, 3, 4, 5, 6, 7. So, we can add possibly one more thing here 8. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, we can sort of put one thing here as well. So, we have eventually 10 equations. So, sorry for the, it is becoming a little untidy, there is a lot of ground to cover. So, we have typically written things like this. So, the first equation, what is the first equation look like? The first equation is just P1 is equal to P2. So, we can write this guy as P1 minus P2 is equal to 0. Okay. So, it is not related to this. So, we can just in place of this thing we write it 1, and in place of P2 we by default all the entries are 0. So, I am not writing it wherever zeros are there. So, I am just writing the non-zero entries. So, this will be minus 1. Okay. This will be minus 1 the first row. Okay. And now, P2 is equal to P3. What does it mean? It means that this will become 1 and this will become minus 1. Okay. So, you have this kind of a thing, and V1 is equal to V2 plus V3. So, what is V1 third equation? V1 is here, V2. So, V2 is your things here. So, so if you go back to this equation, V1 minus V2 minus V3 is equal to 0. So, there will be two negative signs placed in front of V2 and V3. So, we will have minus 1 here and also a minus sitting here. Okay. So, these are the three equations for the first junction laws. We can write the balance of the junction laws also, so that we get done with the junction laws first. So, the fourth equation is your P4. So, this is equal to this, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, P4 is related to P5, which is minus 1 here, and your P4 was also related to P6. So, for the first time we will probably be relating this. So, P4 we can, for the next equation, P4 is equal to, for in the same kind of row, what we will do is that we will relate the P4 thing with the P6 thing. So, this will P4 is equal to P6. So, here it will be not be minus because it is on this side, and everything else is 0 here, 0 here, and then V4 is equal to, V4 is basically your this entry. So, this is equal to this, and this will become minus 1 here. Okay. And here it will be 1. All right. So, we are done with the junction laws here. Now comes the crucial point of putting the transfer matrix in the proper form. So, what I am going to do is that just simply put this thing where these things are there. So, this is the 7th equation. So, it's the 7th row. So, P 2, you know, I for simplicity or for your better understanding, I can sort of just number the rows. Now, P 7 is where your P 2, that is the thing row. So, P 2 minus C 2. So, minus C 2 times P 4. So, so here in place of this entry will become 1, and then your P 4 entry. So, this will be your minus C 2, is not it, and then there will be minus J y 2 sign thing sitting here. So, here there will be minus J S 2 y 2, and what is the other equation that we have? We have V 2, okay. V 2 is your this thing, and minus J sin y 2, you have, you know, such a system, okay. So, we have this equation 7 and 8, and now comes the final bit P 3 V 3 related to P 5 V 5, that is your this thing, okay. So, where do we go from here? P 3 and V 3. So, this requires a lot of patience, I must honestly tell you. So, this will be 1, because once you make an error in the bookkeeping entry, your entire thing will be wrong. So, you will get some absurd transmission loss, you will get to immediately know it. So, that is a good part about it, that you get to know where you are going wrong. So, you can correct it for yourself. So, P 3 and V 3, they are 1 1, all right, and then you have your C 1 things related to the 5th kind of a port. So, here it will be pretty much the same thing, minus C 1 minus J S 1 y 1 minus J S 1 y 1, and this will be minus C 1. Okay. So, we have covered the 10 equations. You know, all the places like where I am marking, you know, all these places where I have not written anything in black color, they are all zeros. So, this connectivity matrix, you can put this in the following form: C matrix, which is the or the matrix that rather than calling it a connectivity matrix, I would call that as a something like a matrix that contains all the information pertaining to the connections between the port, how are the ports related. So, this is a simple tubular connection. So is this. We'll in this week's lecture, we will come across different methods how to arrange these equations. This is just one way of manually doing the stuff, since the first time I am doing for you. So, then all these things, you know, will be zeros. So, now what, and let me call this matrix as B matrix, and actually instead of calling it C, let me call it A matrix, okay. A would be better. So, eventually what we will get is that the big vector spanning P 1 V 1 all the way until P 5 V 5 will be A inverse P and P 6 V 6. So, this is your C matrix. What we will get is that this thing P 1 V 1 and this kind of a inverse B. So, this is finally what we will obtain. P 1 V 1 is related to the things at the port here through the C matrix, where C is A inverse B, and it is analyzed in the following manner. And of course, one can sort of do a lot of algebra, right, at least for this configuration. One can straight away start, you know, eliminating some variables and derive a nice clean analytical formula to get the stuff. But this is just one way of doing network analysis, because for more complicated situations, more complicated muffler analysis, we have to resort to this, and also things like integrated transfer matrix approach, which is nothing but pretty much the same network way of synthesizing things. So, so that is why I suggest that we follow this approach of at least manually arranging things in a A matrix, and then you know, inverting that matrix and all that. So, what we are going to do in the next lecture, that is lecture 2 of week 10, is that derive the transmission loss for such a tube, which is, what is it called? This is called a HQ tube, Herschel-Quincke tube. It has minimum 2 tubes, you can have multiple such tubes, and because of the difference in path difference, we have constructive or destructive interference going on between waves and leading to some non-zero transmission loss. So, note that all these things, the section is, we have a uniform cross section, across this thing. So, in spite of having uniform cross section, you are having non-zero transmission loss in general because of this destructive interference, now at certain frequencies. Now, what we are going to do in the next lecture, that is lecture 2 of week 10, go to MATLAB, write down all these equations in a basically do a MATLAB demonstration of how these equations work, and eventually how do we get to this form, and find out the transmission loss, which is probably going to look something like this. The frequency, this is TL, we have multiple such peaks and something like this. So, it is going to have lot of spikes depending on the length and at certain frequencies. So, we are going to get that and possibly compare the result with some of the previously reported stuff in literature, and let us also analyze one of the analytical formulas and discuss some discrete relationships, frequency relationships. So, we will do that, and then we will move to the more realistic muffler configurations. So, till that time, goodbye, and I will see you in the next class. Thanks.